Okay, so in the friction lab, there was another tricky calculation, and that was the theoretical prediction of what the tension force should be when you're trying to pull a block of a certain mass at an angle theta with a known friction, or there's some friction where you know the coefficient of friction because you had recently measured it. So what must Ft be to pull at a constant speed? So again, this is a force problem, so you want to draw a free body diagram. So that's the mass isolated from its environment, so you're just looking at that mass, and so you don't get distracted by other stuff like the floor or anything like that. So for forces, we have gravity, mg, we have the tension force that you're pulling with, we have the normal force, keeps you from falling through the table, and then the friction force, which opposes the motion. And we can say if we want, just to clarify, we're moving this way, but at constant velocity, so a is 0. So now we can use the forces that we've identified and set up equations for Newton's second law in both the x and the y direction. And I'm just going to draw one thing. The only thing that I like to draw in my free body diagrams besides forces is sometimes you have to draw an angle here or there. Okay, so let's analyze these forces. So in the x direction, the sum of our forces in the x direction has to equal ma, but there's no acceleration, so the sum of the forces has to equal 0. So that means Ft cosine theta minus the force of friction has to equal 0. And in the y direction, we're also not accelerating in y, so the sum of the forces in y has to equal 0. So the normal force minus mg plus, we also have this vertical component of the tension force, Ft sine theta, has to equal 0. Okay, I'm going to put one more equation in. So I'm looking at the two equations that we've come up with. We have this, we have this. We want to find the tension. We also have the normal force, which is an unknown, and then the friction force we haven't identified yet. But we know that we can relate the friction force to the normal force by this expression. So if it's moving, then the friction force is equal to mu sub k, the coefficient of friction, times the normal force. So the friction force is some fraction of the normal force. So this is like, you could consider this a system of 3 equations with 3 unknowns, or you could easily just plug this one in here, and so then it's pretty quickly just becomes two equations with 2 unknowns. So let's start with that. So I'm going to rewrite this equation, but with this expression for the friction force. So Ft cosine theta minus mu k Fn equals 0. And then I can solve for the normal force in this equation. So the normal force is Ft cosine theta over mu k from this expression. Then I can plug that whole thing in here. So Ft cosine theta over mu k minus mg plus Ft sine theta equals 0. Or I'm going to put both terms with Ft together. So Ft sine theta plus cosine theta over mu k equals mg, or ft equals mg over sine theta plus cosine theta over mu k. So that's how you can predict the tension force. Okay, and let's do one sanity check here to make sure this equation makes sense. So for this sanity check, what happens if theta equals 0? So if theta equals 0, that means you're just pulling straight the normal way. So if you're pulling straight and you're going at a constant speed, then there's no acceleration. And so the tension force has to equal the friction force. And let's take this equation and simplify it for the case when theta is 0, then sine theta is going to be 0. And when theta is 0, cosine theta is going to be 1. That's 1 over mu k. And so you find that the tension force has to be mu k mg. And again, when you're in this theta equals 0 situation, everything is much simpler. The normal force is just equal to mg, and so you'd get mu k, the normal force. And that's exactly what you expect